Hello students, how are you all doing? Welcome to our channel physics class, and today we will study magnetization and materials. You know that there are different kind of materials in our nature and how the magnetic property of these materials are influenced, how they get magnetized and what are their different magnetic properties. That is all the topic of today's lecture. So let us go further and start. And please do not forget to comment in the comment box so that I can include much more things that may be interesting to you, or if you have any queries, just write me in the comment box. So let us proceed. Magnetization and materials. So magnetization we always represent with the symbol capital M that we may use for magnetic moment also. But remember, capital M is for magnetization. If you are using, then you can replace magnetic moment with small m. So magnetization is always shown with capital M. Now what is this magnetization M? This is the net magnetic moment per unit volume. So if you divide our magnetic moment, now we will show it with small m, otherwise both will be capital M. So mind this thing, now we are showing our magnetic moment with small m and we divide it with the volume. So the magnetic moment per unit volume. And which magnetic moment we have to take? Say if you are dealing with a system, then you have to take the net magnetic moment. So if we take the net magnetic moment and we divide it with the volume, then we will have the magnetization. So the definition of magnetization is the net magnetic moment per unit volume. Now if you want to know about the units, then this magnetization is magnetic moment, that is the net magnetic moment, and you have to divide it with the volume, and you know the formula for magnetic moment. This is I into A, that is the current into area, and this is the volume. So the unit of current is always ampere, and area will be in meter square, and your volume will be in meter cube. So this meter square cancels out here and we are left with 1 meter. So this is ampere per meter or ampere meter inverse. So the unit of magnetization is always ampere meter inverse. Now let us be more clear about what is this magnetization is. So we take some magnetic material, that is magnetization due to some flow of current. So for example, we take a solenoid. So this is how we draw a solenoid, that we have a hollow cylinder and here we have a number of turns of wires wrapped and the current is flowing through this. So this is a simple representation of a solenoid. And this we take at the axis of the solenoid. And the magnetic field due to solenoid we know as always B is equal to mu naught and I. Mu naught is the magnetic permeability in the vacuum, small is the number of turns per unit length, and I is the current. Now we take it as a hollow cylinder. So if we take that there is a material of non-zero magnetization, that means we have some material which is a magnetic material inside the solenoid, then this magnetic field will be increased. So this is the initial magnetic field, so we denote it with B naught. When there is no magnetic material, this is a hollow cylinder, that is now we are studying till now, then that is the reference magnetic field, B naught is mu naught and I. Now what we do that inside the solenoid we placed a magnetic material. So if there is magnetic material inside the solenoid, it will also get magnetized. So now the total magnetic field will be the sum of initial magnetic field plus the magnetic field due to that magnetization material. This is our initial magnetic field of a solenoid and this is due to the magnetic material we have inside the solenoid. Now the magnetic field due to this magnetic material will depend on magnetization of the material. So this magnetic field is directly proportional to the magnetization of material. So in order to remove the proportionality sign, we introduce a constant, and this constant always in magnetic field or magnetization is always mu naught. So we say that this magnetic field due to magnetization is equal to mu naught m. Mu naught is a constant whose value is 4 pi into 10 to the power minus 7. We already know And if you want to go to the details, you can refer to our lecture. The links are given below. And here mu naught is the permeability of the free space or vacuum. So this is the relation between the magnetic field due to magnetization and magnetization. And also if there is some magnetic field intensity, then that is also added into this term. So we write down this magnetic field due to magnetization will be the sum of this mu naught, and we add this magnetic field intensity into this magnetization. So Bm is equal to mu naught m plus h. So from here we can calculate this h. H is the magnetic intensity or the magnetic field intensity. So this magnetic intensity or magnetic field intensity, full name is magnetic field intensity, but normally we call it magnetic intensity, and it is represented with the symbol H. So from here, if you calculate the value of H, then H is equal to B upon mu naught minus M. So from here, you can see that if you equate the units of both the sides, then the magnetic field, and here is a magnetization, and this is magnetic field intensity. So these two are in addition. That means the units of magnetic field intensity should be similar to that of magnetization. So we can say that the magnetization and magnetic field intensity H has same dimensions. Now what is the relation between this magnetization and magnetic field intensity? Let us find out. This magnetization is proportional to the magnetic field intensity. And again, to remove this proportionality sign, we have to introduce this much. We have to introduce a constant, and this time we cannot use mu naught because we have already used mu naught. So we introduce a new constant that is known as xi. So this constant is xi and h. This is known as magnetic susceptibility. Mu naught is the magnetic permeability. And xi is magnetic susceptibility. So this relation between magnetization and magnetic intensity. So these are the two important relations we have to always remember whenever you are studying about magnetization. So these two relations you should always remember. Now this is magnetic susceptibility. It has different values for different type of magnetic materials. We will go into the details of magnetic materials. The main categories, we can divide them into paramagnets, and dimagnets. So for all these three types of materials, this magnetic susceptibility has different values. It has a high value for the highly magnetic materials, and it has a negative value for the non-magnetic materials, which are not attracted towards the magnetic field. So we will have a quick look of how xi varies for different materials. So in broad, we consider three types of materials. The most important magnetic materials are all ferromagnets, which are strongly attracted towards the magnetic fields, and they have high magnetic properties. We call them as ferromagnets. We'll study them. But for now, we are just studying the value of xi. So that is a brief introduction. Then comes the paramagnetic materials. So these paramagnets also have magnetic properties, but slightly less than in comparison to ferromagnets. And the third type is dimagnets, which are strongly which are not attracted towards the magnetic field. So for paramagnets, Xi will have the highest value, it will have the positive value, and all the large values because these are highly magnetic. For paramagnets, Xi will be positive because these are attracted towards the magnetic field, but this is small in comparison to the ferromagnets, so the value will be small. And dimagnets are not attracted towards the magnetic field, so Xi will have negative value. And small. So this is how it is easy to remember. The Xi for paramagnets is positive and large. Paramagnets is also positive but small. And dimagnets it is negative and small. So we have just derived the relation between the magnetization and the magnetic field intensity. So if you write down for dimagnets, then this will have a negative value. So M is equal to minus Xi of H. That means for dimagnets, M and H magnetization and magnetic field intensity are in opposite direction. Then what for ferromagnets and paramagnets? They will be in the same direction. So for dimagnets, we can write down B is equal to mu naught. So formula M plus H. So we can substitute M is equal to minus XIH. We can write down B is equal to mu naught XIH plus H. So B is equal to mu naught. B is equal to mu naught. H we can take as common. So this is 1 plus Xi. So if it is either a paramagnetic or ferromagnetic material, then we can write down this as H plus XIH because M may be written as XIH. Now in this equation, we can take mu naught and H as common. So this will be 1 plus Xi. And 1 plus Xi we can write down as mu R, that is a relative permeability. So this is mu naught and this we can replace as 1 plus Xi we can replace as mu R, that is the relative permeability mu R, and this is H. So this relative permeability is the ratio of the permeability of any material to the permeability of space. So mu naught into mu R you can write down as mu. So B is equal to mu H. Whenever you are having any magnetization material, then B is equal to mu H. That is again the relation we have already derived, but it is very important. And if you want to know B in terms of H, you can use mu H. And contrary, if you want to know H in terms of V, then H is equal to B upon mu. That will be very much helpful in solving your numericals because till now we have calculated the magnetic field very easily using the Biot-Savart's law or Ampere's circuital law. If you want to know the numericals, I have given the link in the text. I have given the link below, so you can go to that and you can do the numericals. So say for solenoid we were considering, so we know the magnetic field B, so we can do H is equal to B upon mu. Let us see how. So we have just derived H is equal to B upon mu. So for a solenoid, if you are having some magnetic material, then it is B is equal to mu Ni. And if you want to know H, then this is equal to N into I. So for a solenoid, if you want to know the magnetic field intensity, then H is equal to Ni. Whenever we place a magnetic material inside this, then V is equal to mu naught Ni and H is equal to Ni for a solenoid. See, it is that easy to calculate if you know the formula. The next is magnetic properties of materials. So materials we divide broadly into three categories: diamagnetism, paramagnetism and ferromagnetism. So we'll study them one by one. So first we'll study about diamagnetism. The most important property of diamagnetism are that they are not attracted by the magnetic field, even they are repelled by the magnetic field. So if you keep them in external magnetic field, they move from stronger to weaker field. So for these type of magnets, which are diamagnets, these type of materials, the value of Xi, that is magnetic susceptibility, is always negative. So value of Xi is always less than 0 and it may be greater than or equal to -1. So it lies between 0 to -1. It is always less than 0. It may be greater than or equal to -1. And the relative permeability will always be less than 1 and greater than or equal to 0. And mu is always less than mu naught because Xi has a negative value. So these are not attracted by magnetic field. These are not attracted but repelled by magnetic field. And if you keep them in external magnetic field, then they move from stronger to weaker field. Since they are repelled, so Xi is always negative. Always remember that this is repelled, so Xi is negative. So Xi will always be less than 0, but it may be greater than or equal to -1. The relative permeability will also be less than 1. So the relative permeability is less than 1, and you know the relative permeability is mu upon mu naught. So if this is less than 1, then mu will be always less than mu naught. So these are the three relations defined for a diamagnetism. Now, how can you explain diamagnetism? So, to explain the diamagnetism, you go up inside to a diamagnetic material, and if you look at the electrons, then you know that in any of the atom, the electrons is orbiting around the nucleus, and it has some orbital angular momentum. So if this is our nucleus, the positive nucleus, and around this nucleus, if you have an electron which is revolving around this, then it has some orbital angular momentum which is given with L. And since this electron, this is a charge, it is moving, so it also acts as a current carrying loop. So for all the diamagnetic materials or all the diamagnetics, the net orbital angular momentum is 0. Because all those electrons which are having the orbital magnetic moment in the same direction, they slow down, and those in the opposite direction, they speed up. So whenever we apply the magnetic field, then those electrons which are having the orbital angular momentum L in the same direction of the magnetic field, they slow down, and which are having the opposite direction, they speed up. So the net magnetic moment is in opposite direction to the applied field. So that is how, if you keep them in the magnetic field, then the magnetic field is repelled by them. So if this is any of the diamagnetic material, then the magnetic field lines are repelled from it. So this is how we show any of the diamagnetic materials. Whenever these are kept in the external magnetic field, then these are the magnetic field lines. They are repelled through this diamagnetic material. And there are many examples of diamagnetic material. If you go to copper, then copper is a diamagnetic material. Bismuth, lead, which we call as plumbum, that is a diamagnetic material. Silicon is diamagnetic. Nitrogen, then water, H2O is diamagnetic material. NaCl, sodium chloride, and all the superconductors, they shows the property of diamagnetism. That is a very interesting property of all the superconductors. So if you go into the unit of superconductors, you'll find the interesting property of diamagnetism shown by the superconductors. So these are the few examples of diamagnetic materials. So always learn 2 or 3 examples, then how they react in the external magnetic field, what is their magnetic susceptibility, relative permeability and permeability. So from this relation you can find out these 2 relations, and they are repelled, so Xi is negative. And this is the logic why the diamagnetic materials behave as a diamagnetic material. Now move to the second one, that is paramagnetism. So for all the paramagnetic material, the magnetic susceptibility acts as positive because these are weakly attracted by the magnetic field. So it will have a positive value. So the value of Xi will always be greater than 0 because it is positive. And will have the value less than epsilon. The relative permeability will be greater than 1, and less than 1 plus silent. So because this mu r is positive, so if you look up to the relation, mu r is equal to mu upon mu naught. So if mu is mu naught multiplied with a positive sign, so mu is always greater than mu naught. I hope it is clear to you how we find out that mu is less than if it is negative. If mu r is negative, then mu is less than mu naught. And if mu r is positive, then mu is greater than mu naught. And Xi is positive and relative permeability is also positive, having value between these two values. So what is the property of paramagnetism? That if you keep them in external magnetic field, they get weakly magnetized and they move from the region of weak magnetic field to strong magnetic field. That is, they get weakly attracted. So the most important property of paramagnetic materials are they are weakly attracted by a magnetic field. And when kept in external magnetic field, they move from region of weak magnetic field to strong magnetic field. Now, what is the reason for this? Let us go to the reason. The reason is because that for all of the paramagnetic material, all the atoms, they have a permanent magnetic dipole moment of their own. But there is no net magnetization. So when we apply the external field, these individual atomic dipole moment is aligned and pointed in the direction of applied magnetic field. So all the paramagnetic materials, they have a permanent magnetic dipole. But there is no net magnetization. So when these are kept in external magnetic field, then the dipole moment of all these atoms are aligned in the direction of applied magnetic field when they are kept in a uniform magnetic field. And if we keep them in a non-uniform magnetic field, then what happens? Then it moves from weak field to strong field. So if you write down at absolute temperature capital T, we are taking absolute temperature as capital T, then we write down magnetization is equal to V naught is the initial magnetic field and T is the temperature and C is the constant we are using. This is known as the Curie's constant. Now we know the relation between M and H. We have just derived that the magnetization is equal to X time of magnetic field intensity. So if you compare these two equations, then you have the value of Xi as this will be written as C B naught V naught. We can write it down as mu naught H upon T. Right? So if we compare these two equations, then H is common, here M is common, then Xi may be written as C mu naught upon T. C is the Curie constant, mu naught is the permeability of free space, and T is the absolute temperature. And T is the absolute temperature. So for Xi, magnetic susceptibility is proportional to 1 upon T. So C is a Curie constant, so we call this law as Curie's law. This is very important for paramagnetic materials. This we call as Curie's law. And C here is Curie's constant. Curie is the name of the scientist who discovered this. So this is given the name as Curie's constant and Curie's law. Curie's law is that the magnetic susceptibility for the paramagnetic materials is directly proportional to the inverse of temperature. And our relative permeability will also depend on temperature. So for all the paramagnetic materials, you have to remember this law, Curie law, which is very, very important for all of your competitive exam, either objective type or subjective type questions. Curie constant you should always remember, and this Curie's law should be always in your mind for all the paramagnetic materials. Now, what are the examples of paramagnetic materials? Aluminium is a paramagnetic material. Sodium, Na. Calcium. CuCl2, cuprous chloride, and oxygen at standard temperature and pressure at STP. Oxygen. These are the few examples of the paramagnetic materials. So you should always remember 2 or 3 examples of paramagnetic materials. Now go to the most important magnetic material, that is the ferromagnets or ferromagnetic material. So let's go to ferromagnetism, which is the most important of all the magnetic materials. So all the ferromagnetic materials are strongly attracted, so that means their magnetic susceptibility is positive and it is very, very greater than 1 because it has a large value. And relative permeability is also very, very greater than 1. And you know that mu r is equal to mu upon mu naught, and since mu r is very large and positive, since mu r is mu upon mu naught and mu r is very large and positive, that means mu will be very, very greater than mu naught. So these are the 3 relations we can easily define for susceptibility, relative permeability, and permeability for a magnetic material. So these are for the ferromagnetism, and if we keep them in external magnetic field, they are strongly magnetized and they have a strong tendency to move from a weak magnetic field to a strong magnetic field. That is, they are strongly attracted by a magnet or a magnetic field. So their property is that they are strongly attracted by a magnet. And if we keep them in external magnetic field, That is, they get strongly magnetized. Now, what is the reason for this? What happens is for all the atoms which are in a ferromagnetic material, they have a permanent dipole moment and they interact with each other in such a way that they spontaneously align themselves in a common direction over a macroscopic volume. This macroscopic volume, which we call as a domain, and this domain is of around 1 millimeter. It may be around 1 millimeter, and this each domain has a net magnetization. So in the absence of external magnetic field, they have random magnetization from domain to domain, and there is no bulk magnetization. But in the presence of external magnetic field, the domain also orient themselves in the direction of applied magnetic field, and simultaneously domain oriented only in the direction of magnetic field grows in size. And if you keep them in the non-uniform magnetic field, they move from strong magnetic field to the region of highly magnetized field. So for the atoms, if we draw, so this is how we have shown the domain. With the green, you can see these are the different domains, these are the different macroscopic areas, and within each of the domain, all the atoms, their magnetic dipole moment are aligned in the same direction. Like this arrow represents the net magnetization in this domain, this arrow shows the net magnetization in this domain. So within each domain, the net magnetization is in the same direction, but for the different domains, they are aligned randomly. So as a overall, if you see the bulk of a ferromagnetic material, then these are randomly oriented. But if you keep them in the external magnetic field, then what happens? But when you keep in the external magnetic field, then all these magnetic dipole moment of individual domains are aligned in the same direction. So this is for a uniform magnetic field, and if there is a non-uniform magnetic field, then they align to move from the direction of low magnetic field to the magnetic field of region of high magnetic field. Again, this ferromagnetic materials we can divide into two classes: hard magnetic materials and soft magnetic materials. So what is the difference between the hard magnetic materials and soft magnetic materials? So we can divide it into two, hard and soft. So let us understand the basic difference, and then it will be always easier to remember what are the hard magnetic materials and the soft magnetic materials. So all these ferromagnetic materials, they possess this quality. So there is a net magnetization in the presence of external magnetic field. Now if we remove this external magnetic field, if this B naught is removed, if we take this away from here, if this magnetic field is removed, just imagine if we are removing this magnetic field. So again, after the removal of this magnetic field, there is still the magnetization is there. So for all those magnetic material which have a magnetization even after the removal of external magnetic field, they are known as a hard magnetic material. So they have magnetization even after the removal of external magnetic field. Then these are known as a hard magnetic material. So all those materials which have a very good quality of magnetization. For example, if you take nickel, or if you take cobalt, or if you take alnico, this is a combination of aluminium, nickel and cobalt, this is alnico, or leadstone or aluminium, all these are the examples of hard ferromagnetic materials, and these are used as a compass needle because they have a high quality of magnetization, so we can use them as a compass needle. Whereas all those soft ferromagnetic materials, if you remove the externally applied magnetic field, then the magnetization disappears. So the magnetization disappears after the removal of the external magnetic field. If you write on certain examples, then the examples of soft ferromagnetic materials are soft iron, cobalt, nickel, gadolinium. These are the examples of soft ferromagnetic materials. So we can say that for the hard magnetic materials, there is still some magnetization even after the removal of external magnetic field, whereas for the soft ferromagnetic materials, there is no magnetization after the removal of external magnetic field. So this is the basic difference between the hard ferromagnetic material and soft ferromagnetic materials. So after knowing about the hard ferromagnetic materials and soft ferromagnetic materials, let us know down certain things about these three different types of magnetic materials. At high temperature, that means if we increase the temperature, all the ferromagnetic materials behaves as paramagnetic. So we can say that if we increase the temperature, the ferromagnetic properties of the materials convert into the paramagnetic, or the ferromagnetism diverts toward paramagnetism. So what will run out? So at high temperatures, ferromagnetic becomes paramagnetic. So that means if you're having any of the ferromagnetic materials that is having a very high magnetic properties, if you heat it up, even if you can heat your permanent magnet as a bar magnet, then it starts losing its ferromagnetic properties and it start having the properties of a paramagnetic materials. So you can increase the temperature and there will be a decrease in the ferromagnetic or the magnetic properties of a material. The temperature at which this transition happens, we call it as a Curie temperature. We have studied what is the Curie constant and what is Curie's law. So the temperature at which the ferromagnetic materials converts into paramagnetic materials, that temperature we call as Curie temperature. So this is how we define what Curie temperature is. And to denote the Curie temperature, because it is temperature, so we use capital T, and the Curie temperature, so we use suffix C. So whenever you see this TC and you are studying magnetism, that means the temperature at which ferromagnetic will become paramagnetic. And this is called Curie temperature. So that is why we have added a C here. C denotes the Curie temperature. And if you write down the magnetic susceptibility, Xi, then you can write down Xi, this is the Curie constant, upon T minus Tc. So Tc is the transition temperature, T is the temperature given, C is the Curie constant, and Xi is the magnetic susceptibility. And here T is always greater than the Curie temperature. So different materials have different Curie temperature. So different materials have different temperature, where before this temperature, they behave as a ferromagnetic, and above this temperature they behave as a paramagnetic materials. I can give you few examples. For example, if you take the material as cobalt, which is denoted with Cu, then here we can take some materials, and here we can take some Curie temperature, corresponding Curie temperature. And this temperature is in Kelvin. So for cobalt, the temperature is 1394 Kelvin. For iron, that is Fe, ferrum, the temperature is 1043 Kelvin. If you take ferrous oxide, Fe2O3, then the Curie temperature is 893. If you take nickel, which is a very good ferromagnetic material, then the Curie temperature is 631. And if you take gadolinium, then temperature is 317. So these are the different examples of these are the ferromagnetic materials. Before this temperature and above this temperature, they behave as a paramagnetic material. Now, as we know that for the paramagnetic materials, the relative permeability is very greater than 1. We have just studied the 3 types of magnetic materials, and for the paramagnetic materials, mu is very greater than mu naught, and that is why the relative permeability, because we defined relative permeability as mu upon mu naught, right? So this mu is very greater than mu naught. That means mu r should be very greater than 1. Because if this value is large, then if we multiply this mu naught with a large value, then only mu will have a value very greater than mu naught. So this mu r is very greater than 1. And if we take the example of soft ferromagnetic materials, then for all the soft ferromagnetic materials, the relative magnetic permeability mu r is greater than 1000. Then high the value is for the relative permeability. So always keep in mind 3 points, that at high temperature ferromagnetic behaves as paramagnetic, and the temperature which the transition takes place is known as the Curie temperature. And these are the different materials which are their Curie temperature, and this is the relation which is given in terms of the Curie constant and the Curie temperature. And since the relative permeability has a very high value for the ferromagnetic materials, and for the soft ferromagnetic materials, this value exceeds even 1000. So keep in mind these 3 points. So if we are studying about the magnetic properties of the material, then the most interesting materials are ferromagnets. So let us go into some details of these ferromagnets. Because you have seen ferromagnetic materials in types of the permanent magnets. So how can we make permanent magnets? And how can we make electromagnets? So let us go into the detail. First we'll study about is permanent magnets. So how can we make permanent magnets? So first of all, we should know what permanent magnets are. Permanent magnets are which have their magnetic properties throughout. So we know that the ferromagnetic materials are the most important materials which have the most magnetic properties. So all the ferromagnetic substances which retain their ferromagnetic properties at room temperature for a long period of time, then we call them as permanent magnets. So let us define what are permanent magnets. So all those ferromagnetic materials which retains their ferromagnetic properties at room temperature for a long period of time. The next question is how to make permanent magnets. So first and the most easiest way is to heat any of the ferromagnetic materials. It may be iron or it will be a steel. Then you take a rod of iron or steel and you stroke it with one end of a bar magnet. So all the magnetic properties of the bar magnet are transferred into this ferromagnetic materials. If you do it a large number of times, then that steel or iron rod will too have a magnetic properties, and it will become a permanent magnet. So that is easily we can make a permanent magnet. And if you want to observe in daily days any example of how this magnetic properties are transferred, you just take most commonly available at your home are the safety pins which are made up of steel. And if you keep them in touch with the permanent magnet for some times, and then they start behaving as a magnet. They retain the magnetic properties for some time, and they have all the magnetic properties, and if you touch them to other iron or steel, they get stuck it up. So that is how you can see just a daily example of how the magnetic properties are transferred. Second easiest way to make a permanent magnet is that we place a ferromagnetic rod in a solenoid and we pass a current through it. So due to the current flowing into it, it will create a magnetic field. And the magnetic field of the solenoid magnetizes the rod. So again, we have transferred the magnetic properties into a ferromagnetic materials. So these are the two simple ways through which we can transfer the magnetic properties into a ferromagnetic materials, and they will retain their ferromagnetic properties. They will retain the magnetism for a long period of time. So that is how we can make easily any of the permanent magnet. Now, what the qualities of permanent magnet should have? That means we have to choose which kind of material so it will behave as a good permanent magnet. Let us find out the properties. So if you want to have a good permanent magnet, and how we can select suitable materials for permanent magnet. So for this we have to know about the two quantities. So for this we have to focus on three quantities. First is the permeability mu. Then two other quantities are retentivity and corrosivity. Permeability, we know that how easily it allows the magnetic field lines to pass through it. So all those materials we want to have a permanent magnet should have a high permeability. So the materials should have high permeability. Now about the retentivity and corrosivity, we still don't know what are these two quantities. So for a moment, note them down, then we'll study, and then I'll make it again clear that why we should have these high values. So the materials should have high retentivity. So in most easy words, if you want to understand the word retentivity, that means it is the power of the material to retain the magnetic field. That is why it is known as retentivity. So how much strongly it is retaining the magnetic field, it is retaining the magnetization, that is known as the retentivity. And the materials should have high corrosivity. So in simple words, if you want to understand the word corrosivity, that means how strong magnetic field we have to apply, or how strong negative magnetic field we have to apply if you want to remove the magnetic property, if you want to remove the magnetization. That is known as corrosivity. We will understand these two terms for the ferromagnetic materials right after this. So it is how easily it is. So we can say, so that the magnetism is not erased by how much negative magnetic field we have to apply, how much negative field we have to apply in order to remove the magnetization. So it should be a high value so that our magnetization is not erased by stray magnetic fields. So the material should have high permeability, first thing. Second, it should have high retentivity. Third, it should have high corrosivity. So these are the three qualities. If the material is processing, then it can behave as a very good permanent magnet. So which are the materials which have all these three qualities? So which are the materials which have all these three qualities? We can take them as steel, or soft iron, or an alloy of aluminium, nickel and cobalt, we call as alnico, or we can take cobalt. So if you go for steel, then they have comparatively small retentivity. Yes, so retentivity is good, but if you see comparison to other ferromagnetic materials, other permanent magnetic materials, then comparatively it is small. So comparatively the retentivity of steel is small. And if you go to the soft iron, then the comparatively corrosivity is small. So that you should always remember. It is very useful that steel we are going to draw one graph that is known as the BH curve or the hysteresis loop. But you should always remember that for the steel, the retentivity is small comparatively, and for the iron, corrosivity is small comparatively. These two are the very important thing, and this should be much easy to remember after we study hysteresis loop. But always remember this. Steel, comparatively small retentivity, and soft iron, comparatively small corrosivity. So always remember, always remember these two things. So in order to understand what is corrosivity, what is retentivity, which one is having small, which one is having greater, let us go to this interesting property of all the ferromagnetic materials. And this property we call as hysteresis. So let us study what is this very important topic hysteresis is. In order to understand the hysteresis, what we do, we take any of the ferromagnetic material and we keep this ferromagnetic material in external magnetic field. So we draw a graph and on x-axis we take H, which is the magnetizing field, and B is the magnetic flux density. Right, so we have written B and H here. So now what we do, if we have a ferromagnetic material and it is in the external field, so if we increase the magnetization field, then the magnetic flux density also increases. So as we increase the magnetization field H, the magnetic flux density B also increases. So if we go from this point or region O, then our magnetization flux density increases as such. And after reaching to this point, it saturates, because you see that here our magnetization is increasing, then the corresponding magnetic flux density is also increasing. It is a non-linear region, but after coming to this point, it reaches to a linear region. That means on increasing the magnetizing field, our magnetic flux density will not increase anymore. So this region we call as the saturation region. So this point we call as point A. So on increasing the magnetizing field, our magnetic flux density increases as OA and it saturates. Now what we want to do? We want to reduce this magnetizing field. So when we reduce this magnetizing field, then it does not follow the reverse path AO. It goes from point A to point B. This is point small b. So when we reduce the magnetizing field, the magnetic flux density reduces from A to B. Now here you can see that although the magnetization field H is 0, but the magnetic flux density is not 0. That means the ferromagnetic material is still retaining the magnetic property. So this property of retaining the magnetic field or the magnetic flux density, it is the retained field, so we call it as retentivity or remanence. So we can write down that at point small b. So here you can see H is equal to 0. The magnetizing field is 0, but the magnetic flux density is not equal to 0. That means the ferromagnetic material is still having some magnetic properties, which are shown by the magnetic flux density. So this retaining magnetic field is retentivity or remanence. So we can see that at point B, H is 0 but B is not 0. So this value of capital B from O to B, so this value of capital B we call as retentivity or remanence. And now if we reverse the magnetization field in the reverse direction, that is in the negative direction, the opposite direction to the present direction. Initially we have applied the magnetization field in the positive direction and now we are applying it in the reverse direction. So we proceed towards negative value of magnetization field. Then our graph proceeds like it goes down from B to C. So this is point small c. So on increasing the magnetization field in the reverse direction, in the opposite direction, our graph grows from B to C. Increasing the magnetization field in the reverse direction, in the opposite direction, it is shown with a curve BC. Now at point C, as you can see, the magnetic flux density is 0, but the magnetizing field has some value which is the negative value. That means that in order to make the value of B, in order to make the value of magnetic flux density 0 for any of the paramagnetic material, we have to apply the magnetization field in the opposite direction. So this amount of magnetization field which we have to apply, this negative value of magnetization field, which can make the magnetic flux density 0. This is known as coercivity. So this value of H, which is the negative value at point C, is called as coercivity. So we can say at point small c, so here you can see that B is equal to 0, but H is not equal to 0. So this negative value of H we call as coercivity. Now if we increase the B further in the negative direction, in the opposite direction, then our magnetic field is also increased in the negative direction and it reaches to the saturation value. And our graph goes from point C to point D as such. So this is point D and this is the saturation value. So on further increasing the negative value of the magnetization field, our magnetic flux density will not increase. Now again we reverse the direction of the magnetization field, then our magnetic flux density starts increasing and it goes from point D to point E. And on further increasing the value, the graph reaches from point E to again point A. So as we can see that if we increase the magnetization field in the opposite direction, so the magnetic flux density also increases and there is a saturation of the magnetization field. So there is a saturation of the magnetic flux density which is shown as E to A. So again we reaches to the saturation state. So as we can see that initially when we increase the magnetization field, then the magnetic flux density increased from point O to point A. But when we again make the magnetization field in the positive direction, then it does not retrace the path itself. It does not follow again the path O to A. It follows the path from E to A. Right? So this loop you can see in the blue color, this loop we call as a hysteresis loop. Hysteresis means lagging behind, as you can see through the graph that this graph is lagging behind this original one. So this loop we call as hysteresis loop, and this is a peculiar property of all the ferromagnetic materials. They all make a hysteresis loop. So let us go once again. When we increase the magnetization field, then the magnetic flux density increases, then it reaches to saturation at point A. Then after saturation, we cannot increase further, so we decrease the magnetization field, then it comes to point B. So here our magnetization field is 0, but the magnetic flux density is not 0. So this we call as retentivity. This is the residual magnetism in the ferromagnetic material. On further decreasing the magnetization field, it comes down to point C. Now what you have to do here, you can see that the value of magnetization field is negative. It is on the negative side of x-axis. So this is the negative value or the opposite side of the magnetization field we have to apply in order to make the B 0. That means for any of the ferromagnetic material, if you want to remove all the magnetic flux density, if you want to remove the magnetic property, then we have to apply some negative value of magnetization field. This value we have to apply, which values from O to C. This we call as coercivity. And now on further increasing the magnetization field, for a negative value, again it reaches to the saturation at point D, and now we start again increasing the magnetization field in the positive direction, then it increases from D to E and E to A. So there is a complete loop which is formed by a ferromagnetic material, and this loop we call as a hysteresis loop. So for all the ferromagnetic materials, two things are of much important. One is the retentivity, residual magnetism, and one is the coercivity, negative magnetization field we have to apply to make the magnetization zero. So now hysteresis loop is clear to us. What is retentivity and what is coercivity is also clear to us. So you can see at point B where the magnetization field is zero, but the magnetic flux density is not zero. There is still some magnetic property we call as retentivity or remanence. And at point C where the magnetic field density is zero, that means the magnetization is zero, but we have to apply this H. So this negative magnetization field we call as coercivity. So if you want to make a permanent magnet, now you can make it very much clear that the retentivity should be high. That means that even if you are not applying some magnetization field, it should have some magnetism. So for all the permanent magnets, retentivity should be high. Also the coercivity should be high. That means that if you want to remove the magnetization, then you have to apply a large amount of magnetization field, and that to negative value of magnetization field. So for all the permanent magnets, these retentivity and coercivity both should be high. And we call this as hysteresis because hysteresis means lagging behind. So this lagging behind of the loop is given with the name hysteresis loop. And this magnetic field we have to apply, it may be of the order of around say 90 ampere per meter. That may be the value of coercivity. And it may retain the magnetic flux density may be of the order of 1.5 Tesla. Right? So all the ferromagnetic materials, they make this hysteresis loop, but for all the different materials, this loop differs. Some may have the high coercivity, some may have the high retentivity or the low coercivity. So if you want to make a graph for the two ferromagnetic materials, then we can proceed as such. Let us see hysteresis loop for two different ferromagnetic materials. So here I have taken the magnetization field at on the x-axis, that is in ampere per meter, and on the y-axis we have the magnetic flux density that shows the magnetization. So this is in Tesla. Now these are the two hysteresis loop I have drawn. First is the blue one and second is the green one. And now we have to find out that which hysteresis loop corresponds to which ferromagnetic material. So we have seen in the permanent magnets. So one of this graph is for steel and other is for the soft iron. So how would you find out that these are the two ferromagnetic materials which are having this hysteresis loop? So as you remember, for the permanent magnets we have done that steel has comparatively small retentivity, and retentivity is given as the residual magnetism. So here you can see here the magnetization field is zero and this is the value of residual magnetism. So if you compare for the blue one or the green one, then the blue hysteresis loop is having small retentivity. So we can say that this blue graph is for steel and this is having the high retentivity, but if you come to the coercivity, then this green one is having the small coercivity. That means in order to remove the magnetization, we have to apply comparatively small negative magnetization field to remove the magnetization. So this green graph corresponds to soft iron. So we can write down as such that this blue one is for steel which has a small retentivity. So we can write down as such that this blue one is for steel which has a small value of retentivity. So here you can see that this blue one is having small retentivity, and this green curve, the green hysteresis loop is for soft iron because it has a small coercivity. Here you can see the value of coercivity. So for the steel, coercivity is comparatively high and retentivity is comparatively low. But for the soft iron, you can see that the retentivity is comparatively high, but the coercivity is comparatively small. So our blue curve is for steel and the green one is for soft iron. So just by looking at this hysteresis loop, we can find out which is having the high retentivity, which is having the small retentivity, which is having the high coercivity, or which is having the small coercivity. So that is that easy. If you know the terms, if you understand the terms, then you can apply the physics and you can easily write them down. And I hope it is clear to know that why for a permanent magnet we need high coercivity as well as high retentivity. Right, that's all for today. And if you want to understand such very interesting thing and in a very simple manner so that the basics are clear, you need not always grasp them, but you should understand and you should apply your logic. You should use the basics of physics, and then you can solve them very easily. So if you want to go for more such interesting lectures, more such interesting basics in the physics and learning them in the best possible way, then like and share and subscribe to our channel Physics Class so that you will receive notifications and you will be continuously updated for all the new lectures, all the interesting new lectures that will increase your knowledge of physics and make you more smart in physics. Thank you.